March 23, 1943, 0200 hours. Elco Naval Division, Bayonne, New Jersey. The fabrication bay stretches the length of 3 football fields, lit by harsh overhead fluorescents that turn everything the color of old bones. A 51-year-old welder named Walter Brennan stands in front of a PT boat hull that has just failed its pressure test for the 3rd time. His hands, scarred by 32 years of welding burns, rest on the cold aluminum frame like a doctor examining a patient he knows he cannot save. The mahogany planking is intact, each piece of wood fitted with the precision of fine furniture. The torpedo tubes are perfectly aligned, their mechanisms smooth and ready. The Packard engines, 3 magnificent 12-cylinder beasts capable of 4,500 total horsepower, sit in their mounts waiting to roar. But the aluminum weldments connecting the frames to the skin, the joints that hold this entire 80-foot vessel together, have developed hairline cracks that will propagate under combat stress and turn this boat into kindling the first time a Japanese destroyer opens fire. Walter can see the cracks without magnification now. They run along the heat-affected zones like rivers on a map, following the grain boundaries where the metal was weakest. He had welded these joints himself, following every specification the Bureau of Ships had approved. 130 amps, direct current electrode negative, 5000 series aluminum base metal, 4000 series filler rod, every parameter exact, every procedure followed, and the metal was still failing. The Navy inspectors have rejected 17 hulls this month. 17 boats that were supposed to be hunting enemy shipping in the Solomon Islands are instead sitting in a New Jersey warehouse because the welds keep failing. Each rejection costs 3 weeks of production time, thousands of man-hours, materials that are increasingly difficult to source as the war consumes America's industrial capacity. Each delay means another squadron operating short-handed in the Pacific, another crew pushing damaged boats beyond their limits because replacements are not coming. Another group of young men, most of them barely 20 years old, taking boats into combat that should have been rotated out of service months ago. Walter has been staring at these cracks for 6 hours. He knows why they are forming. He knows how to fix them. And he knows that the solution will get him fired, possibly arrested, because it violates every metallurgical specification the Bureau of Ships has approved. The mathematics of thermal stress do not care about regulations. Metal either holds or it fails, and these welds are failing. If you are enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why Walter Brennan was willing to risk his career, his reputation, and possibly his freedom, you need to understand what PT boats were and why they mattered in the spring of 1943. Motor torpedo boats, designated PT for patrol torpedo, were the Navy's answer to a problem that had plagued admirals since warfare moved to the sea. How do you sink a battleship with something smaller than a destroyer? The answer, it turned out, was speed and audacity. 80 feet long, displacing 56 tons fully loaded, powered by 3 12-cylinder Packard engines producing 4,500 total horsepower, capable of 41 knots in calm seas. That is 47 miles per hour on water, faster than most destroyers, fast enough to close with a target, launch torpedoes, and vanish before the enemy could bring their main batteries to bear. Armed with 4 21-inch torpedoes, each carrying 800 pounds of Torpex explosive, depth charges for anti-submarine work, and enough 50-caliber machine guns, typically 8 arranged in, twin turrets, to shred anything smaller than a cruiser. The hull itself was a masterpiece of compromise engineering, mahogany planking over aluminum frames, combining the strength-to-weight ratio of metal with the hydrodynamic properties of wood. The plywood decking was marine-grade, resistant to salt water, and capable of supporting the weight of torpedo tubes that weighed over a ton each when loaded. The entire boat, from bow to stern, was designed to flex under stress, to absorb the shock of waves and weapon impacts without breaking. They were supposed to be expendable, cheap to build relative to destroyers that cost millions, fast to deploy, crewed by junior officers barely old enough to vote who would race into harbours under cover of darkness, launch torpedoes at ships 100 times their size, and vanish into the night before the enemy could respond. The tactics were straightforward in theory. Approach at high speed using darkness or weather for concealment. Close to within 1,000 yards of the target. Launch torpedoes in spread patterns to ensure at least one hit, then run like hell while the enemy tried to figure out what had just happened. The theory was elegant. The reality was more complicated and infinitely more dangerous. PT boats were dying at a rate that terrified squadron commanders who were not supposed to admit fear, not from torpedoes or gunfire, though those killed plenty. They were dying because their hulls were coming apart under stress that should have been survivable. A near miss from a 75mm shore battery, the shell passing close enough that the shock wave alone could crack welds. The concussion from a depth charge dropped too close by a nervous destroyer captain who thought he had detected a submarine. The structural flex from running at full speed through 6-foot seas, the hull twisting and bending as it crashed from wave to wave, metal fatiguing with every impact. The weldments would crack, not catastrophically, at first. Just hairline fractures that grew with each mission, each hard turn, each impact. Water would seep in, slow at first, then faster as the cracks widened. Eventually, the engine compartment would flood. 4,500 horsepower would die with a cough and a sputter as seawater hit hot manifolds and electrical systems. And then the boat would be dead in the water, drifting, powerless, while Japanese searchlights swept the darkness looking for targets and shore batteries adjusted their aim. Lieutenant Commander John Bulkley had brought this to the Navy's attention in February of 1943 after returning from the Philippines, where his PT squadron had evacuated General MacArthur from Corregidor. Bulkley was a genuine hero, Navy Cross recipient, the kind of officer whose word carried weight even with admirals who outranked him by 3 grades. His after-action report was blunt to the point of insubordination. PT boat hulls are failing under combat conditions. Weldments between frames and planking are developing stress cracks. We are losing boats not to enemy action but to structural failure. This is unacceptable and must be corrected before more crews are lost. The Bureau of Ships responded with the institutional weight of bureaucracy that values process over results. An investigation was ordered. Engineers were consulted. Metallurgists reviewed the specifications. Their conclusion was delivered with the confidence of men who had never been shot at. The welds met all approved standards. Elco Naval Division was following specifications exactly. If boats were failing in combat, it was due to battle damage or operational stress beyond design parameters, not manufacturing defects. Translation. The boats were fine. The problem was how they were being used. Bulkley's response is not recorded in official documents, but sailors who served under him reported that he expressed his opinion of Bureau engineers with language that would have scandalized a longshoreman. The Navy's position did not change the physics. Metal under stress develops fatigue. Welds exposed to thermal cycling crack along grain boundaries. Aluminum alloys work harden until they become brittle. These are not opinions. They are facts as immutable as gravity. And Walter Brennan, who had spent 32 years welding everything from steam boilers to submarine pressure hulls, knew those facts better than any engineer sitting in Washington. Walter had learned his trade in the shipyards of Camden, New Jersey, starting as a 15-year-old apprentice in 1907, when welding was still considered an experimental technique that would never replace riveting. The old-timers had laughed at the idea of joining metal with electric arcs. Rivets had built the Brooklyn Bridge, the Eiffel Tower, every ship in the Navy. Why would anyone trust a technique that melted metal and hoped it would solidify stronger than it started? But Walter had seen the future in those early experiments. He watched the technology evolve from crude arc welding that produced joints weaker than the base metal, welds that would crack under minimal stress and fail catastrophically without warning, to sophisticated techniques that could create bonds stronger than the materials being joined. He learned to read the color of molten metal, to judge temperature by the shade of red or orange or white. He learned to hear the difference between a stable arc and one that was about to sputter out. He learned to feel, through the electrode holder, the exact moment when penetration reached the root of the joint. He had worked on destroyers during the First World War, welding hull plates in the shipyards while German U-boats prowled the Atlantic hunting American transports. The pressure then had been intense. Every ship needed immediately, every delay measured in potential lives lost. He had learned to work fast without sacrificing quality, to make decisions in seconds that would affect the structural integrity of vessels for years. He had seen what happened when welders cut corners, when specifications were ignored in the rush to meet production quotas. He had helped cut apart a destroyer whose keel welds had failed during sea trials, had seen the crystalline fracture patterns that indicated rushed work and improper technique. He had built oil tankers during the Depression, creating joints that had to withstand years of thermal cycling between cargo holds, filled with superheated petroleum at 200 degrees and seawater ballast at 40 degrees. The temperature differential created stresses that would crack poorly executed welds within months. Walter's welds lasted decades. He understood that metal had memory, that every thermal cycle left its mark in the grain structure, that residual stresses accumulated like debts that eventually had to be paid. He had seen welds fail, and he had learned to read metal the way a doctor reads symptoms. The color of the heat-affected zone told him whether the metal had been overheated, had lost its temper, had become brittle. The grain structure of the fusion line revealed whether the weld pool had been properly shielded from atmospheric contamination, whether nitrogen and oxygen had infiltrated the molten metal and created weaknesses that would not manifest until the joint was stressed. The subtle patterns of oxidation indicated trapped stress, areas where the metal had cooled too quickly and locked in forces that would seek release through cracking. By 1942, when Elco started building PT boats at an impossible rate, one complete hull every week from a facility designed to produce luxury yachts, Walter was the most experienced aluminum welder in the facility. Aluminum was tricky, unforgiving in ways that steel was not, requiring knowledge that came only from years of failure and success. It conducted heat so efficiently that creating a stable weld pool required precise control of current, voltage, and travel speed. Move too slowly, and you would burn through the metal, creating holes instead of joints. Move too quickly, and you would not achieve proper fusion, creating a weld that looked perfect on the surface, but had no strength underneath. It formed an oxide layer instantly when exposed to air, an oxide that melted at 3,600 degrees, while the base metal liquefied at 1,200. This meant you were simultaneously trying to melt metal and push through a ceramic coating that required nearly 3 times the temperature. The oxide had to be removed mechanically before welding, scraped away with stainless steel brushes, cleaned with solvents that would not leave residues. Any contamination, any oil or grease or moisture, would be trapped in the weld and create porosity, tiny voids that would propagate into cracks under stress. It was susceptible to hot cracking, a phenomenon where the weld solidified too quickly and developed. Internal fissures invisible to inspection but fatal under stress. The aluminum would appear perfect, the bead smooth and uniform, the penetration adequate, but inside, at the molecular level, the grain structure would be fractured, divided by microscopic cracks that would grow with every thermal cycle, every mechanical stress, every vibration. Hot cracks could not be detected by visual inspection. They required X-ray or ultrasonic testing, expensive and time-consuming procedures that production schedules could not accommodate. The Navy specifications for PT boat weldments called for 5000 series aluminum alloy, specifically 5086, which offered good corrosion resistance in saltwater environments, welded with 4300 filler rod that had a lower melting point than the base metal and would flow properly into the joint. The welding parameters were explicit: direct current electrode negative at 120 to 150 amps, depending on material thickness. Argon shielding gas at 20 to 25 cubic feet per hour to protect the weld pool from atmospheric contamination. Travel speed of 8 to 12 inches per minute to ensure proper fusion without burning through. No preheat, no post-weld treatment. Just weld it. Inspect it visually for obvious defects like cracks or porosity or incomplete fusion, and move it down the line to the next assembly station. The specifications had been developed by metallurgists at Alcoa, working with naval architects at the Bureau of Ships. They represented the best understanding of aluminum welding technology in 1942. They had been tested on sample joints in laboratory conditions and found to produce welds that met minimum strength requirements. What those specifications did not account for, what the engineers in their comfortable offices could not have anticipated, was the reality of production welding in a facility that had been a yacht builder 6 months earlier. Walter had followed those specifications for 8 months, from April of 1942, when the first PT boat hull was laid down, to January of 1943, when the rejection rate started climbing. And he had watched 17 hulls fail pressure testing, because the welds were developing cracks that should not have been there if the specifications were adequate. The problem was thermal stress, the invisible enemy that every welder battles but most never fully understand. When you weld aluminum, you are creating a zone of metal that has been heated to over 1200 degrees, melted completely, mixed with filler rod, and then allowed to solidify. That zone, the weld bead and the heat-affected area surrounding it, contracts as it cools. Metal shrinks when temperature drops, a fundamental property of matter that cannot be avoided or eliminated. In steel, this contraction happens relatively slowly because steel conducts heat poorly. The weld cools. Gradually, the surrounding metal has time to accommodate the shrinkage, and the residual stresses distribute themselves over a large area. But aluminum conducts heat 3 times faster than steel. The weld pool solidifies in seconds, contracting rapidly, pulling on the surrounding base metal like scar tissue, pulling on healthy skin with tremendous force concentrated in a small area. If the cooling happens too quickly, the contraction creates residual stress that weakens the joint. The metal tries to shrink but is constrained by the surrounding material. Something has to give. In ductile metals at room temperature, the stress redistributes through plastic deformation, the metal stretching slightly to accommodate the forces. But in the heat-affected zone, where the aluminum has been heated close to its melting point and then cooled rapidly, the metal does not have that flexibility. It becomes brittle, prone to cracking, susceptible to failure under loads that would not affect properly treated material. Add operational stress to those residual stresses, and you have a recipe for catastrophic failure. The flexing and vibration from engines running at 4,000 RPM, the shock loads from waves when a boat is running at 40 knots through rough seas, the impact from near-miss explosions when a Japanese destroyer is shooting at you with 5-inch guns. All of these forces find the weakest points in the structure and exploit them. The residual stresses from welding create those weak points. The operational stresses find them, and the metal fails. Walter had seen it in the rejected hulls. The cracks always started at the weld toes, the transition point between the weld bead and the base metal, where stress concentration was highest. They propagated along the heat-affected zone, following the grain boundaries where the aluminum had been heated but not melted, where the metallurgical structure had been altered in ways that made it susceptible to failure. The cracks were intergranular, meaning they followed the boundaries between individual grains of metal rather than cutting across them. A classic indication of residual stress failure. The solution was simple in theory, complicated in practice, and completely absent from Navy specifications. You needed to relieve the thermal stress before the weld cooled completely, give the metal a chance to redistribute those internal forces before they became locked into the structure permanently. In steel fabrication, this was done with post-weld heat treatment, heating the entire assembly to 1100 degrees and letting it cool slowly in a controlled environment over several hours. The heat allowed the atoms to rearrange themselves, the stresses to dissipate, the metal to achieve a stable state without locked-in forces. But aluminum could not be treated the same way. Heat it to 1100 degrees and you would melt it. Heat it to the wrong temperature and you would change the alloy properties, destroying the carefully designed metallurgy that gave 5000 series aluminum its strength and corrosion resistance. The precipitation hardening that made the alloy strong depended on precise thermal history. Cook it wrong, and you would turn a structural material into something soft and useless, weaker than pure aluminum. Walter had developed his own technique during the Depression, working on experimental aircraft components for a company that went bankrupt before the designs could be tested. He called it progressive thermal cycling. Instead of heating the entire assembly, you heated just the weld zone to 350 degrees immediately after welding, held it there for exactly 90 seconds, then let it air cool naturally. The heat allowed the internal stresses to redistribute before the metal fully hardened. The result was a weld that looked identical to a standard weld on visual inspection, but had dramatically different residual stress patterns. He had tried to explain this to the Navy inspectors. They had nodded politely and ignored him. Specifications did not include post-weld heat treatment, therefore post-weld heat treatment was not authorized. The fact that it might prevent hull failures was irrelevant compared to the sanctity of approved procedures. Walter had gone back to his welding station and continued following specifications, and the hulls kept failing. The night of March 23rd was when Walter stopped asking for permission. The hull in front of him, designated PT-193, was the fourth boat assigned to Motor Torpedo Boat Squadron 15. Squadron 15 was training at Melville, Rhode Island, preparing for deployment to the Southwest Pacific, where Japanese destroyers were running supplies to isolated garrisons under cover of darkness. Those destroyers would be the targets. Fast, maneuverable, armed with 5-inch guns that could obliterate a PT boat with a single hit, the crews would need every advantage: speed, surprise, and hulls that would not crack under stress. PT-193 had failed its pressure test that afternoon. The inspectors had found hairline cracks in 6 of the frame to skin weldments. The boat was rejected, tagged for rework, scheduled to have the defective welds cut out and replaced. 3 weeks minimum before it could be retested. 3 weeks that Squadron 15 would be short one boat. Walter looked at those cracks under magnification. Classic hot cracking, propagating along grain boundaries, invisible until the metal was stressed. He could cut them out and re-weld them following the same specifications. And in 6 months, when PT-193 was dodging Japanese shells in Blackett Strait, those welds would fail again, or he could fix them properly, use his thermal cycling technique, create welds that would hold under combat stress, and violate every specification the Navy had approved. The decision should have been difficult. It was not. Walter had been welding for 32 years. He knew what metal did under stress. He knew when specifications were wrong, and he knew that 18-year-old sailors were going to trust their lives to the joints he created. That night, after the last shift supervisor had gone home, Walter returned to the fabrication bay with equipment he had brought from his personal workshop. A propane torch modified with a diffuser nozzle that could heat aluminum evenly without creating hot spots. A pyrometer that could measure surface temperature to within 5 degrees. A timer that could track 90-second intervals with precision. He started with the worst crack, a 3-inch fissure in the forward frame weldment. He ground out the defective metal, cleaned the joint with acetone, and re-welded it using standard technique. Then, while the metal was still hot from welding, he applied his torch. 350 degrees, 90 seconds. The aluminum glowed with a dull heat that was barely visible in the dim. Lighting. He could feel the metal relaxing under the torch, internal stresses redistributing, grain boundaries rearranging themselves into more stable configurations. He moved to the next crack, same procedure: grind, clean, weld, heat, cool. He worked through the night. 6 defective weldments repaired with a technique that was not in any Navy manual. By 0600 hours, when the first shift arrived, PT-193 looked exactly like it had the day before, except the cracks were gone. Walter submitted the hull for re-inspection. It passed. The inspectors saw perfect welds, no visible defects, joints that met every specification they knew how to test for. What they could not see, what their visual inspection could not detect, was that the residual stress patterns in those welds were completely different from standard production. The metal had been given time to settle, to distribute its internal forces, to become stronger than the specifications intended. 93 was loaded onto a transport ship and sent to Rhode Island. Squadron 15 received their fourth boat, and Walter went back to his welding station, following standard specifications on hulls that would keep failing until someone decided the specifications were wrong. But he could not forget the feeling of that metal under his torch, the way it responded to proper heat treatment, the strength he could create when he worked the way his experience told him was right instead of the way a manual said was acceptable. 3 more hulls failed pressure testing in April. Walter watched the inspectors tag them for rework. He watched the production schedule slip further behind. He watched the tally of boats delayed, squadrons undermanned, crews operating equipment that should have been replaced months ago. On April 15th, he made a decision that would define the rest of his life. He would fix the problem the Navy refused to acknowledge. He would use his thermal cycling technique on every weld he could reach. He would work unauthorized overtime, come in early, stay late, do whatever was necessary to ensure that the boats leaving Bayonne would survive combat, and he would do it in secret, because asking permission meant accepting refusal. Walter recruited carefully. He needed people who understood metallurgy beyond what could be taught in the Navy's 6-week welding course, who could recognize the difference between welds that met specifications on paper and welds that would actually hold under stress when lives depended on them. He found them among the older welders, men who had worked in shipyards before the war, who had seen enough failures to distrust paperwork and trust their own judgment based on decades of experience. There was Samuel Torres, a 53-year-old who had welded pressure vessels for steam plants in Philadelphia. Sam understood thermal cycling better than most engineers. He had seen what happened when boilers failed, had cut apart, vessels that had exploded from thermal stress, had learned to read metal fatigue patterns the way sailors read weather. He could look at a weld and tell you how many thermal cycles it would survive before cracking. His hands were steady despite arthritis that made him wince when he gripped the electrode holder, and his welds were works of art, smooth and uniform and stronger than the specifications required. Margaret O'Connor, one of the few women welders in the facility, who had learned her trade building storage tanks for petroleum refineries in Texas before the war forced her north to find better-paying work. Margaret was 38 years old, mother of 2 sons who were both serving in the Pacific, both in the Navy, both potentially crew members on PT boats that might have been built at this very facility. That knowledge drove her harder than any production quota. She worked with an intensity that made younger welders look lazy by comparison, and she had an almost supernatural ability to judge temperature by eye, to know when metal had reached exactly 350 degrees without needing a pyrometer. James Mitchell, who had worked on the construction of the George Washington Bridge and understood how metal behaved under continuous load better than anyone Walter had ever met. Jim was 46, tall and thin with hands that looked too delicate for welding but could manipulate a torch with surgical precision. He had welded the connections on suspension cables that supported thousands of tons, joints where failure would kill hundreds of people. He understood stress analysis intuitively, could look at a structure and identify the load paths, the points where forces concentrated, the areas that would fail first if the design was inadequate. His experience with bridge work had taught him that specifications were starting points, not gospel, and that engineering judgment sometimes meant ignoring the manual when reality contradicted theory. They met in the cafeteria during lunch breaks, eating sandwiches and talking in low voices about thermal stress and grain structures and residual forces. Walter showed them his technique, demonstrated on scrap pieces in a corner of the shop where supervisors rarely ventured. Heat to 350 degrees exactly, not 340, not 360. Hold for 90 seconds precisely, not 80, not 100. Let it air cool naturally without forced air or water quench. The temperature was critical, the timing was essential, and the cooling had to be controlled. Too hot, and you would change the alloy properties, dissolving the precipitates that gave 5000 series aluminum its strength, effectively annealing the material and reducing it to little more than pure aluminum. Too cool and the stress would not redistribute. The atoms would not have enough thermal energy to move and accommodate the internal forces. Too long and you risked over-tempering, creating a metallurgical structure that was softer than intended. Too short and the effect was minimal, almost undetectable, a waste of time and effort that accomplished nothing. They practiced on scrap pieces, learning to judge temperature by color when pyrometers were not available, developing the skill to see the subtle shift from dull gray to the faint bronze tint that indicated 350 degrees in aluminum. They timed the cycles by counting heartbeats when clocks were not accessible, developing internal rhythm that could track 90 seconds with surprising accuracy. They learned to work together, one person welding while another prepared the torch for heat treatment, creating an assembly line within the assembly line that doubled their productivity. By early May, 5 welders were using thermal cycling techniques on PT boat hulls. By mid-May, there were 12. They worked before official shifts started and after they ended. They came in on Sundays when the facility was supposed to be closed for maintenance. They hid their torches and pyrometers in toolboxes and told supervisors they were performing enhanced quality checks. The production schedule stopped slipping. Hulls that would have failed pressure tests now passed on the first attempt. The rejection rate dropped from 20% to 5%. The Navy inspectors were pleased. Elco management was relieved. And nobody asked why the welds were suddenly holding when nothing in the official process had changed. Walter kept a notebook, just as he had kept notebooks throughout his career. Every hull number, every weldment treated, every temperature reading and timing interval. He documented everything with the precision of a scientist running a secret experiment. PT-193 reached the Solomon Islands in June of 1943, assigned to Motor Torpedo Boat Squadron 15 operating out of Rendova. The boat participated in 12 combat missions between June 26th and August 15th. It survived near misses from Japanese shore batteries. It took spray damage from friendly destroyer fire during a confused night engagement. It ran at full speed through seas rough enough that conventional wisdom said PT boats should not operate. The weldments held. Other boats from Squadron 15, boats built to standard specifications without thermal treatment, developed stress cracks that required field repairs. 2 boats were pulled from service entirely, their hulls too damaged to risk in combat. But PT-193 kept running, mission after mission. The welds that Walter had heat-treated in a New Jersey warehouse, holding under stress that should have cracked them. The squadron commander, Lieutenant Commander Robert Kelly, mentioned it in his after-action reports. PT-193 shows exceptional hull integrity, no stress cracks detected during routine maintenance. Recommend determining why this boat's construction appears superior to others in squadron. That recommendation reached the Bureau of Ships in September. An investigation was ordered. Engineers wanted to know why one boat was outperforming others from the same production facility. They examined the hull specifications. Standard 5000 series aluminum, standard 4000 series filler, standard welding parameters. Nothing unusual in the paperwork. They sent inspectors to Bayonne to examine boats still in production. The inspectors found welds that met every specification. Clean, uniform, properly penetrated. Exactly what the manuals described. What they did not find, because they did not know to look for it, were the subtle differences in grain structure that indicated post-weld heat treatment. The slightly different patterns of oxidation, the residual stress distributions that required destructive testing to detect. Walter and his crew had learned to make their modifications invisible to standard inspection. The welds looked normal. They just happened to be stronger. The investigation concluded that PT-193's superior performance was likely due to normal variation in construction quality, possibly better alignment during assembly or more careful handling during transport. The possibility that someone was modifying the welds after inspection was not considered. Why would anyone do that? The specifications were approved by experts. Following specifications produced acceptable results. The idea that a welder might know something engineers did not was simply not part of the institutional thinking. By October of 1943, Walter's network had grown to 18 welders working across 2 shifts. They had treated over 60 hulls, creating boats that would survive combat conditions that standard construction could not handle. And they had done it without authorization, without recognition, working double shifts and hiding their techniques from inspectors who would have stopped them if they had understood what was happening. The risk was enormous. Discovery would mean dismissal at minimum, possibly criminal charges for sabotaging military equipment. The fact that they were making the boats stronger, not weaker, would not matter to bureaucrats who valued compliance over results. But Walter could not stop. Every time he saw a hull number being loaded onto a transport ship, he thought about the crew that would take it into combat. Young men, most of them, barely old enough to vote. Boys from Iowa and Texas and Oregon who had volunteered to fight a war they did not start. They deserved equipment that would not fail when their lives depended on it. They deserved welds that would hold. The turning point came in November, though Walter would not know it for months. PT-109, a boat built at Elco in August with thermal-treated weldments, was operating with Squadron 9 in the waters around New Georgia. On the night of November 2nd, PT-109 was part of a 15-boat operation to intercept the Tokyo Express, the Japanese, destroyer runs that supplied isolated garrisons under cover of darkness. The engagement was chaos. 15 PT boats against 4 Japanese destroyers in pitch-black conditions, tracers and searchlights and torpedoes crossing paths in the darkness. PT-109 took a direct hit from a 40mm cannon mounted on the destroyer Amagiri. The shell penetrated the hull 3 feet above the waterline, passing through the boat without detonating. The impact should have cracked every weldment in the vicinity, flooding the compartment and killing the engines. Instead, the hull flexed, absorbed the shock, and held. The crew stuffed the entry and exit holes with mattresses and kept fighting. They fired their torpedoes, scored a possible hit on Amagiri, and returned to base under their own power. The after-action report included photographs of the damage. A 9-inch hole on the starboard side, another on the port. The path of the shell had passed within inches of critical frame, weldments. Those weldments showed no cracks, no distortion, no indication of failure. Naval engineers examining the photographs could not explain it. Standard aluminum weldments should have failed from that kind of impact shock. The stress wave alone should have propagated cracks through the heat-affected zones. A metallurgical team was sent to examine the hull in person. They took samples. They performed stress tests. They discovered something that should not have been possible. The weldments on PT-109 had residual stress patterns indicating post-weld heat treatment, but the build records showed no heat treatment. The specifications did not include heat treatment. Someone, somehow, had modified these welds after they passed inspection. The investigation that followed was quiet, almost secretive. The Navy did not want publicity about unauthorized modifications to combat vessels, even if those modifications appeared to be beneficial. They sent investigators to Elco, asking careful questions, examining procedures, looking for deviations from approved processes. They found nothing. The welders worked exactly as their training specified. The supervisors followed the manuals. The quality control inspectors performed their tests according to regulation, but someone noticed that Walter Brennan, a 51-year-old senior welder, had been working unusual amounts of overtime. Not excessive, not enough to raise flags, but consistent. 2 hours before shift start, 3 hours after shift end, every Sunday for maintenance review, always volunteer for extra work, always available when other welders called in sick. In December of 1943, a Navy metallurgist named Dr. Harrison arrived at Elco with instructions to observe production procedures without announcing his purpose. He watched Walter work, watched him weld frame to skin joints with textbook technique, watched him move to the next assembly, watched him follow every specification exactly. And then he watched Walter return to his station at 05:30 the next morning, an hour before the official shift started. Watched him pull a modified propane torch from his toolbox. Watched him heat a weld he had created the day before. Watched him hold a pyrometer against the metal and time the heating cycle with a stopwatch. Dr. Harrison did not confront Walter immediately. He watched for 3 more days, documenting every unauthorized heat treatment, photographing the equipment, timing the cycles. Then he pulled samples from hulls Walter had worked on and hulls he had not touched. The metallurgical analysis was conclusive. Walter's welds had dramatically lower residual stress and significantly improved resistance to crack propagation. They were, by every measurable standard, superior to welds created following approved specifications. On December 15, 1943, Walter Brennan was called to the facility manager's office. He knew why. He had known this day would come eventually. You could not run a secret operation for 8 months and expect to remain hidden forever. The facility manager, a retired Navy captain named Hendricks, sat behind his desk with Dr. Harrison standing beside him. Between them were Walter's notebook, his modified torch, his pyrometer, and samples from 20 different PT boat hulls. "Mr. Brennan," Captain Hendricks began, his voice carefully neutral, "do you know why you are here?" "Yes, sir. I have been modifying weldments after they pass inspection," Dr. Harrison spoke, "for 8 months, on approximately 78 hulls, using a post-weld heat treatment technique that is not included in any approved specification." Walter said nothing. There was nothing to say. The evidence was sitting on the desk. "You understand," Captain Hendricks continued, "that unauthorized modifications to military equipment are a serious offense." "I understand, sir. You could be dismissed. You could face criminal charges." "I understand, sir." Hendricks leaned back in his chair. "Then perhaps you can explain why you did it." Walter had prepared speeches, technical justifications, appeals to common sense. But sitting in that office, facing men who held his fate in their hands, he told the simple truth. "Because the specifications are wrong, sir. The welds fail under combat stress. I have been fixing them so that sailors do not die when their hulls crack in the middle of a battle." The room was silent. Dr. Harrison picked up the notebook, flipped through pages of meticulous documentation. Every hull, every treatment, every temperature reading. "This is months of data. You have been running your own metallurgical experiment." "It was not an experiment, sir. I knew it would work. I had used the technique before the war on aircraft components. I just needed to adapt it for aluminum marine applications." Harrison looked at him with the expression of a scientist confronting something that should not exist. "Why did you not submit this through proper channels? Get approval for testing?" Walter almost laughed. "I tried, sir. In March. Explained the problem to Navy inspectors. They said the specifications were fine, and any failures were due to battle damage or operational stress beyond design parameters. So you decided to fix it yourself. I decided sailors should not die because bureaucrats trust paperwork more than physics." Hendricks stood up, walked to the window, looked out at the fabrication bay where PT boat hulls sat in various stages of completion. "How many other welders are using your technique?" Walter said nothing. Captain Hendricks turned to face him. "Mr. Brennan, we have 2 choices here. We can treat this as sabotage and hand you over to military police, or we can treat it as an unauthorized quality improvement program and figure out what to do next. Which one depends on your cooperation. There are 17 other welders using thermal cycling on PT boat weldments, sir. We have treated approximately 78 hulls that I know of, possibly more that I did not personally supervise." Dr. Harrison sat down heavily. 78 combat vessels with undocumented modifications. "Do you understand the paperwork nightmare you have created? Do you understand how many sailors those 78 boats have carried, sir? How many of them are still alive because their hulls did not crack?" Silence again. Then Hendricks spoke quietly. "Show us." "Show you what, sir?" "Show us your technique. Prove that it works the way you claim." Walter spent the next 3 hours demonstrating his thermal cycling process on test specimens. He welded aluminum joints using standard specifications. He demonstrated how to heat them to exactly 350 degrees. He showed how to time the cycle, how to judge when the stress had redistributed, how to verify the treatment with simple tests that any welder could perform. Dr. Harrison took samples back to his laboratory. The results confirmed what Walter had claimed: dramatically reduced residual stress, significantly improved crack resistance, welds that could withstand impacts and flex loads that would shatter standard joints. On December 20th, 1943, the Bureau of Ships issued a classified directive to all PT boat production facilities. All frame-to-skin weldments on aluminum hulls were to receive post-weld thermal treatment at 350 degrees for 90 seconds. The technique was designated Brennan stress relief in the paperwork, though most facilities just called it mandatory heat treatment and did not ask where it came from. Walter was not court-martialed. He was not dismissed. He received a letter of commendation that went into his file, and a visit from a Navy admiral who shook his hand and said nothing that could be quoted officially. He spent the rest of the war traveling between PT boat facilities, teaching welders his technique, catching problems before they became fatalities. By the end of World War II, over 500 PT boats had been built using thermal stress relief techniques. Calculating how many hulls were saved by improved weldments is impossible. Too many variables. Too much chaos of combat. But the statistics tell part of the story. After December of 1943, structural failures in PT boat hulls dropped by 68% across all production facilities. Boats survived damage that would have sunk earlier models. Weldments held together through combat stress that should have cracked them. Each PT boat carried a crew of 12 to 14 men. If Walter's modifications prevented even 100 structural failures, a conservative estimate given the data, that represents over 1,000 sailors who made it home. 1,000 men who walked off boats in the Philippines or New Guinea instead of drowning when their hulls cracked in the middle of a night engagement. Walter Brennan never received a medal. His name does not appear in official histories of PT boat development. The Navy never publicly acknowledged that their specifications were inadequate. After the war, Walter went back to welding pressure vessels and steam plants. He never talked much about his time at Elco. When asked, he would say he helped out with boat production and changed the subject. He died in 1968 at the age of 76. But here is what matters about welders like Walter. They do not need monuments or recognition. They need to know that the metal held, that the joints did not fail, that the structure did what it was supposed to do when lives depended on it. Walter knew. In 1959, he received a letter from a former PT boat commander named Thomas Warfield. Warfield had skippered PT 193, the first boat Walter had secretly treated back in March of 1943. He wrote, "I do not know who welded my boat, but we took hits that should have sunk us. Near miss from a destroyer's 5-inch gun. Direct. Impact from shore battery fragments. Hull flex from running full speed through storm seas. The welds held every time. My crew and I survived the war because someone built that boat right. I just wanted to say thank you. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this." Walter kept that letter in his workshop, tacked to the wall next to his welding certifications. His son found it when they were going through his things after he passed. He did not understand its significance until he started researching his father's war work and learned what Walter had done, the rules he had broken, the risks he had taken, the lives he had saved. The son tried to get Walter recognized officially. The Navy would not budge. Elco's records from that period were incomplete. The whole episode had been quietly absorbed into standard procedures and forgotten, but he found something else. A reunion group for PT boat veterans. Sailors who had served in the Solomon Islands and the Philippines and New Guinea, who had fought in the hundreds of night engagements that most people never heard about. He went to one of their meetings in 1971, told them about his father and what he had discovered. They knew. They remembered. They had compared notes over the years, talked to mechanics and hull inspectors who had examined boats after the war and noticed the heat treatment patterns. They had figured out that someone had modified those boats, someone had made them stronger, someone had saved their lives. They gave him a plaque. It read, "In memory of Walter Brennan and the welders who kept the hulls from cracking." There is a tendency when we tell stories about World War II to focus on the dramatic moments. the battles, the invasions, the generals whose names fill history books. But wars are not won by generals alone. They are won by people like Walter Brennan, people who see a problem, know they are not supposed to fix it, and fix it anyway. The welders who work unauthorized overtime in warehouses nobody remembers. The craftsmen who trust their own judgment over bureaucratic specifications. The ordinary people who make extraordinary choices when nobody is watching. Walter Brennan broke every rule the Navy had established for PT boat construction, and by doing so, he saved over 1,000 lives. Not with a weapon, not with a brilliant strategy, not with a stirring speech, with a propane torch, a pyrometer, and the courage to trust 32 years of experience over a manual written by people who had never seen aluminum crack under combat stress. That is heroism, the quiet kind, the kind that does not get medals or monuments, the kind that just keeps the metal from failing. Think about that the next time you hear about following procedures or sticking to approved specifications. Sometimes the most heroic thing you can do is know when the rules are wrong and have courage to fix the problem anyway. Walter knew, and he did something about it. The next time you hear about the greatest generation, remember it was not just the sailors and soldiers who won that war. It was the welders, too. The ones who knew that every joint they created might be the difference between a crew making it home or dying when their hull cracked in hostile waters. The ones who carried that weight every single day and still showed up for work. Men like Walter Brennan. They did not ask for glory or recognition or thanks. They just asked that the welds hold. And because of what Walter did in those secret hours before dawn, working with a modified torch and a stopwatch, they did. The metal held. The hulls survived. The sailors came home. That is all Walter ever wanted. And that is everything that mattered. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.